Hi, so this is going to be for Chem 1211. This is chapter 3, and we're going to be in sections 3.4, 3.5, and 3.7. We're skipping section 3.6. I like to do that after I've talked about electron configurations. So first, we'll just make a quick note of the photoelectric effect. You don't need to worry about solving using this equation, just knowing what the photoelectric effect is. Basically, electrons are emitted when a certain threshold is met when you hit a metal with photons. So essentially, we will hit a metal surface with some photons, and then sometimes it will eject electrons, and we pick them up. In this test here, we're picking them up with a positive electrode, and we're measuring how many electrons, electron volts we get. So each electron gives us an electron volt. So let's say we hit it with violet light. We'll see that we do get some electrons put off in this situation. The meter is showing that we do have some voltage. If we hit it with what looks like red light, it is showing no current. And if we hit it with like just brighter red light, it still shows no current. The point of this being is that the wavelength of the light matters, and the frequency of the light matters. There's a threshold frequency that we have to hit in order to kick electrons out. The red light has a lower frequency. Even if we increase the intensity of it, it still is a lower frequency. And so it's the violet light that has a higher frequency that would give us the electron coming off in this case. So every metal is going to have some sort of threshold frequency where the electrons will come off at a certain point. It's similar to how solar panels work, and so the photons are hitting. It's way more complicated, but essentially photons are hitting a material, and the material is ejecting electrons. That electron traveling is what makes electricity. We're going to be talking about the Bohr model and how Bohr made his model based on light that he sees. So basically, we talked about this a little bit, but basically he had a tube full of hydrogen gas. He excited it, and he looked at the offput through a prism, and it separated into these specific bands of light. And these specific bands of light correspond to certain wavelengths of visible light, certain wavelengths of color. And so basically, what we're assuming here is that the same thing is happening. We're hitting the hydrogen with some sort of energy source, and the electrons are being moved around. When the electrons are moved around, they are somehow giving off these specific wavelengths or frequencies or energies of light. We can use this formula to figure out how far the electron traveled. So N is going to be called your energy level. And so the difference in the energy levels, the inverse of the difference in the energy levels, is going to give us the inverse of the wavelength produced by that energy level change. And then this is a constant that we can plug in that will help make our math work. Let's talk about these energy levels. And so if this math kind of comes from the idea that we have different energy levels around the nucleus being positive, and the electrons, the little negative electrons, are hanging out in these different energy levels. And so as the electrons move around and they change energy, sometimes they give off energy. The energy level, or the energy in that level, is expressed by this formula and equation, where the energy level is N. And you start out at 1, and you go increase by 1 as you move higher. Now, one thing that's not really shown here is that as you move forward with your energy levels, you actually get closer to the previous energy level. So 4 is closer to 3 than 3 is to 2. And 5 is closer to 4. than 4:3. So as we keep going up, we get closer and closer together, kind of like a stadium where you're more on top of the person in front of you than if you were at the bottom of a stadium, for example. So what we're looking at with electron transitions is that electrons are moving around between these different energy levels. We give it energy, electron moves up. When the electron moves back down, because it wants to be closer to the positive nucleus, it releases some energy. And we can calculate how much energy it releases by looking at the wavelength of energy that's released. We can consider these electron transitions and notice that the lines are appropriate now, like the big gap between 1 and 2, smaller gap between 2 and 3, etc. And so as we move farther away from the nucleus, the differences in the energy levels is smaller. And so that's what I was trying to depict here. This is the same thing, except if we just took like a cross section, like just studied one side of it. So if we give the electron energy up to an infinite number of energy levels, we can expect that if it goes from 2 to 1, it's giving us ultraviolet light. If it goes from 3 to 1, so if it goes per minute anywhere down all the way down to 1, that's a lot of energy. So higher energy is going to give us ultraviolet. So it's going to emit higher energy when it comes down. The electron absorbs energy and moves up, and when it comes down, it gives off energy. We can actually see only the Balmer series, and that's what is shown here, called the Balmer series. You don't need to know the names of these, but more distance traveled, higher energy. So violet would be our highest energy. Less distance traveled, lower energy. So red would be our lower energy. And then we have even lower energy, smaller distances in the infrared. And so we get these energies out when electrons go from high to low. If an electron is in a state higher than it should be, higher than normal, then we call it an excited state. And a ground state will be the lowest level state that it can be in. So we can think about the math. What's the change in energy if an electron goes from 3 to 2? So 3 to 2. And we can decide what the change in energy is going to be. And then we can assign that to a certain color or a certain wavelength. So you're going to want to use this formula. I think they have it actually. So we're going to use we're going to take this formula here. We're going to take this one and we're going to kind of combine it with the Rydberg equation and make it a little easier to use. So we're going to use this formula, but we're going to change it just a little bit. You're not going to have to memorize this for a test. You'll see this in the homework. I think it's good algebra practice, so I do keep it. So the change in energy, or delta E, is going to be equal to this amount of joules, and then we're going to have the N final squared minus the N initial squared, where F is final and I is initial. And they have this wrong. This should be initial here. So if we're going from our final, so N final is 2 and N initial is 3, we can calculate what the change in energy is going to be when we go here. And of course, if we know the change in energy, we can then later plug in to get our frequency. And then we can later correspond to a wavelength. So why don't you try this math and see what you get. So hopefully you pause and try the math. And this is going to be how you put the work in. So final minus initial, and we should be getting this number. So this is the number of joules associated for 3 down to 2. Now you could take that and you could plug it in to find the wavelength. And you could plug it in to find the frequency. So you could know, hey, that's red, because you will see a wavelength and it will correspond to the wavelength of red light. So that's basically what Bohr was speculating when he saw these lines. And of course, there's other people that worked on this, obviously, because they have their names in here. But the electrons must be moving in discrete ways that will give us these specific lines. So he essentially came up with these energy levels and that electrons are moving around in these specific energy levels. And it's negative energy change, not because it's negative energy, but because it's losing energy, right? It's going from higher energy to lower energy. So we're losing energy. So it's not that there's negative energy, it's that the energy change is 3.0 times 10 to the negative 19 joules, and the energy change is just in the losing of energy, not the gaining of energy. So the negative sign is just for the direction of energy flow, losing or gaining, not necessarily for negative energy. So electrons are studied. We now have an idea, historically, we have an idea that electrons are not just willy-nilly hanging around outside the nucleus. They're actually hanging around in specific places. We call those orbitals, like specific orbits around the nucleus. And then de Broglie came along and said that I think that electrons are behaving as waves as well as matter. And there's a lot of work gone into this. This is really a big subject in physical chemistry if you're going all the way for chemistry. You do not need to worry about this, but essentially there's a constant, and then we have some, let's see. So your m is your mass, and then you have your this should be your velocity. Um, you don't need to worry about this. Don't worry about this, but I want you to think about electrons moving around in their particles, but they kind of have a wave-like movement as well. But don't worry about what these mean. You don't need to worry about this formula. But this helps explain this stability. So why doesn't an electron just always go down to level 1, right? Like why doesn't it, go how can it be stable if it's up here, right? So describing it as moving around in waves allowed chemists at the time to accept that if they had this sort of wave function, they can be more stable. The next thing that kind of came up with was the Heisenberg uncertainty principle. Because we have this change in velocity, x being the location here, we cannot know both the location and the velocity at the same time, or momentum at the same time. What we can get is a probability map for where it might be based on the information we know. So because electrons are constantly moving, and because they're moving in these wave patterns, we are uncertain if we know where it is, we don't really know how fast it was going, or its momentum. And if we know its momentum, then we don't really know where it is anymore. So we can't know both at the same time. That's called the Heisenberg uncertainty principle. Again, you don't need to worry about the math. When we start to get talking about electrons moving as waves, you may be recalling that we know that photons, light, moves as waves and as particles. So electrons are actually doing the same thing. Quantum mechanics is a model that we have to best describe this. And we're moving now to our current understanding of atomic structure. Schrodinger developed quantum mechanics and a wave equation to help describe electrons' waves. These are called the Schrodinger equation. They're wave functions. We can get all into this. This is a whole big line of work, especially if you go into physical chemistry, you'll get into this. But this is the same Schrodinger of Schrodinger's cat, right? And then so the wave function is describing how the wave is moving around where in the location that it is, essentially. You don't need to worry about solving the wave function. You will do that in Chem. And then another person came along and said that the square of the wave function actually describes what we call an orbital, which an orbital is where we're going. This is where we're going to get into, where we're going to stay. The three-dimensional region where probability is high. So imagine if I sprayed some cologne or perfume, there is a space in which we would have high probability of finding dots of the liquid, right? We have a few different probability maps where we think electrons are. So the shapes of the orbitals depend on, I want you to think about it like, you can think about it like baseball pitch projections. Like each point is a place where a pitch was thrown, right? So a probability map of where like a pitcher's where the ball is going to go for that particular pitcher is kind of similar here. Don't worry about all these graphs and numbers and distributions and all that kind of stuff. Basically, there's a sweet spot for distance from the nucleus that will find things depending on the energy level. What do you need to know? You need to know this information. So everything else we've been talking about is just kind of building up to like how do we historically get all of this information? You don't have to memorize any of these steps or names of people or anything. What you need to know is an s orbital is spherical. So an s orbital happens at every level, and this is just showing you a cross section, but an s orbital is spherical, so kind of like this. Like this one would be considered an s orbital, and it goes in energy levels. And so energy level 1 has an s orbital, and then energy level 2 has an s orbital that encompasses the 1s, and then energy level 3 has an s orbital that encompasses the 1s and the 2s. So it's kind of like stacking dolls, right? It is layers. So we can see the distance. This is how we know these things. Distance from the nucleus is high, is down here in the 100 range or whatever. And then we have some electrons here in the 1s, and then we have a lot of electrons in the 2s. And then we have some in the 1s, and then we have the 2s, and then we have the 3s, right? And so here we're kind of seeing how electrons are being filled. The distribution of electrons is showing that we have specific locations, but it's not exactly just a straight line. It's not all electrons are exactly this far away from the nucleus, right? Because they go in waves, they have a range. Again, don't need to worry about these graphs. You just need to know S is a sphere. P orbitals are these dumbbell shapes. So we have px, py, and pz, and then you put all three of them together and you get this kind of composite view. So don't worry about these numbers quite yet. We'll talk about these later. But so first shell, energy level 1 has only S. Energy level 2 has S and then also has a P. And a P comes with all three, and electrons are floating around. You have 2 electrons in each, so they can be here, or they could both be here and here and here, or they're just kind of floating around in this area. So we'll probably have electrons in this area if you have a p orbital. Now, energy level 1 has just S, energy level 2 has S and P, energy level 3 has S, P, and D. And as you can imagine, we get even more complicated. So we just kind of take 2 p orbitals and put them together in all kind of directions. And then we have this one that looks like he's got a hula hoop on. Again, don't worry about these numbers. But we have, these are probability maps where we think electrons might be. And so think about what our atomic model might look like at this point, right? So I might have an atomic model that would have, all right, we got an s orbital, that's 1s, and then we have 2s, and then after 2s we can add in 2p, and 2p comes with 3 of them. And then we have 3s, and then we have 3s, and then we have 3p, and then we have, technically we have 4s, and then we have 3d, and 3D has all these shapes in it, right? And so you can imagine that it's just very hard to view what we think an atom looks like once we get here. So a lot of times we'll actually just default back to the Bohr model, even though we know it's not 100% correct. They're not just floating around in those straight lines. They're actually probably in these shapes around the nucleus, but those are really hard to depict. So you'll see us, I say us as chemists, use the Bohr model to explain stuff a lot, even though we know that's not true. And then if we get to energy level 4, we have S, P, D, and F. If you want to Google F orbitals, they get all kinds of crazy. There are 7 of them. So we go from one type of shape, a sphere, 3 shapes, X, Y, Z, 5 shapes for D, and then 7 shapes for F. And when we look at the periodic table, we will be able to know how we can memorize this or use the periodic table to memorize it instead of outright memorize it.